Today I'd like to talk about how birds evolved flight. Flying is a superpower, and us humans are amazed with flight, from superheroes to airplanes. And yet, the birds we see every day accomplish this phenomenon seemingly effortlessly. So how exactly did modern birds come to evolve this superpower? As you might know, birds were not the first to evolve flight. Flight has independently evolved at least 4 times in the Earth's history, first with insects, then flying reptiles called pterosaurs, then birds, and most recently, bats. The earliest bird we know of, a dinosaur called Archaeopteryx, was quite unlike modern birds and lacked some of their features. There has been much debate about whether or not Archaeopteryx was even capable of powered flight, but it's generally agreed that it was capable of at least weak powered flight. Flight has evolved so rarely because it is quite the feat to accomplish. In order to accomplish flight, an organism must balance 4 forces: lift, weight, thrust, and drag. An organism must create enough lift to counteract its weight, and it must create enough forward thrust to counteract its drag. And this is no easy feat, and birds have some pretty amazing acceptations that allow them to conquer these forces. An acceptation is a feature that was used by an organism's ancestors for one reason, but was then co-opted in the evolutionary process for an entirely different purpose. The first of these acceptations is feathers. Feathers were initially evolved in theropod dinosaurs as a method of heat regulation and display. This means that everyone's favorite, T-Rex, was probably covered in a sort of proto-feather. These feathers were slowly changed over generations until early birds had developed the asymmetrical feathers we see in modern birds. And birds use these to create lift in flight. The next acceptation that allowed birds to fly is their hollow bones. Birds' Saurischian ancestors used these hollow bones as part of their cardiovascular system, allowing them to reach enormous sizes. This is one adaptation that allowed birds' sauropod cousins, the long-necked dinosaurs, to reach the titanic sizes that they did. Birds, however, co-opted this feature to reduce weight, making it easier to fly. The third important acceptation birds have is actually their flight motion. One group of birds' ancestors, the dromaeosaurs, used a forward grasping motion to capture their prey. This was the precursor to birds' flapping motion, and the bones and the muscles used in dromaeosaur prey capture would later go on to be critical in flight. The last important acceptation for bird flight is endothermy, or warm-bloodedness. Endothermy was originally evolved by theropod dinosaurs, which allowed them to regulate their body temperature and therefore thrive in a wider variety of environments. Birds, however, use this adaptation for an additional purpose, as the higher metabolism of endothermy allows them to burn the energy necessary for flight. So how, then, did early birds actually use these acceptations to flap their wings and start flying? Despite all the evidence we have, there are quite a few different theories, each with their own supporters and critics. Generally, though, there are 4 theories with the most support from the scientific community. These theories are the tree-down theory, the ground-up theory, the where theory, and the pouncing proavis theory. The arboreal, or tree-down theory, is probably the one that makes the most sense to people at first glance. This theory states that birds' ancestors jumped between branches of trees, and later from tree to tree, and feathers, gliding, and later powered flight evolved from a need to hone this skill. The main criticism of this theory, though, is that almost all organisms that evolve flight in this way are quadrupedal, whereas early birds were bipedal. While seemingly a small problem, the evolutionary mechanics of this can be quite problematic. The cursorial, or ground-up theory, is exactly what the name sounds like. Birds evolve flight from the ground up. This theory posits that early birds, like Archaeopteryx, use their wings to assist in running. And then they may have used their feathers as a sort of net to catch insects as prey. This theory is supported by the strongly bipedal nature of early birds, but it's unclear if there would have been enough selective pressure to increase lift that would lead to the powerful flight of birds today. The wing-assisted inclined running, or WARE hypothesis, is quite an interesting one. This hypothesis states that early birds likely used their wings and feathers not to generate flight, but to create downforce, allowing them greater traction as they ran, letting them run up otherwise impossible surfaces. The wear hypothesis has quite a lot of evidence in modern birds, as most birds utilize wear from quite a young age. In fact, using wear is even more energy efficient than flight for getting to most perches. This means early birds, and even their feathered theropod ancestors, may have used their feathers to evade predators and chase prey up trees and cliffs that otherwise would be impossible to climb. This means it's quite possible that feathered theropods like Velociraptor here would have been able to chase you up an almost vertical cliff. Yikes. The last theory I'd like to talk about is the pouncing proavis theory. This theory states that birds evolved flight as ambush predators, pouncing on their prey from elevated surfaces like rocks or trees. Now, this theory at first glance seems very similar to the arboreal theory. However, there's a very important difference. In the arboreal model, the main selection factor that would have led to powered flight is speed or efficiency of the jump between trees. In the pouncing proavis model, however, the primary selection factor that would have been improved by natural selection until flight was achieved is locomotor control. This means that early birds would have swooped down on their insect prey, and natural selection would have favored the individuals that could swoop down with more control. One of the main ways they would have controlled their swoop is their control of lift. Thus, the development of this locomotor control would eventually have led to individuals with more control of lift, thereby allowing them to initiate powered flight. All of the theories presented today have their strengths and weaknesses, but from the research I've done and the professors I've spoken to, it seems that two stand out as the most plausible. The wear theory and the pouncing proavis theory tend to have the most evidence from the fossil record and physical studies, and the most support from the scientific community. This means that early birds likely used some combination of pouncing and running up steep inclines to hone their superpower of flight, until eventually we came to the friendly, flying tweeters we know and love today.